Okay, the first thing we're going to take a look at is we're going to take a look at these exponential functions. These are the first set of transcendental or non-algebraic types of functions. We're going to define an exponential function as any function f of x equals a times b to the x power. Okay. Now, a is going to be any real number as long as a is non-zero. Okay, so we're going to say a is a real number, but a cannot be 0. And obviously, if a was 0, it would just be a constant function. And we're going to say that b is a real number as well. We're going to say that b cannot be 1. If b was a 1, or if b was a 0, we would end up having a constant function as well. Okay? So one of the first things we should probably look at is we should probably look at the graph of an exponential function. Let's take, for instance, a basic exponential function. Okay? Let's take a look at the graph of f of x is going to be equal to 2 to the x power, a very basic exponential function. One of the ways that you may remember to graph a function is to use a table of values. Okay? Let's go over a little bit. Let's make a table of values for this exponential function, and then we're going to go ahead and graph it. From the graph, we may be able to see its domain and its range and any other sort of properties, like maybe some asymptotes, any intercepts, etc. For the table of values, here's my x and then my f of x. You may remember that it's probably best to pick some positive numbers, some negative numbers, and then throw 0 in there to kind of see what's going to happen with this function. So I'm going to use -2, -1, 0, 1, and 2 as my values for the exponential function. Let's start from the bottom and work our way up, because it's probably a little bit easier. Okay. I'm going to substitute 2 back in for the x, and that's fairly easy. We know that 2 squared is 4. I'm going to substitute 1 back in for x. 2 to the first is 2. Okay. Some people think 2 to the 0 is going to be 0. Hopefully we remember from our basic algebra that anything to the 0th power is always 1, except 0 to the 0, called an indeterminate form, which we'll talk about later. 2 to the -1. Some students think 2 to the -1 is -2. It is not. Remember, negative exponent means you flip it over. You take the reciprocal. So this is going to be 1 over 2 to the first, otherwise known as a half. And then finally, 2 to the -2 is going to be 1 over 2 squared, otherwise known as 1/4. That's our table of values. Hopefully that's fairly easy for you guys at this point. Let's go ahead and graph this function and see what the function looks like, and then maybe start to talk about some of the key characteristics of the function. Here's my Cartesian plane. I'm going to quickly plot the points. -2, 1/4, left 2, up 1/4. So maybe 1/4, just a little bit above the axis right there. -1, 1/2, left 1, up a half. 0, 1/2, I'm sorry, 0, 1, excuse me, I was looking diagonally. 0, 1 just goes up 1 unit. And then we have 1, 2. And then finally we have 2, 4. If we play connect the dots, this is approximately what our exponential function is going to look like. I'm going to cheat a little bit and fill in the dot here. Okay. All right. Maybe not the best looking exponential function in the world. Hopefully you don't discriminate against my inability to construct things. Let's take a look at the domain for this. Domain is all the x values. It seems like that it's going to keep going left forever. It seems like it's going to keep going right forever. Okay? It doesn't look like it's going to end, even though it kind of seems like it's getting slower going to the right. Going up, it's going to go up very quickly. So the domain for this function is from minus infinity to positive infinity. For the range of this function, it doesn't look like it's going to dip below the x-axis. Or in other words, the y value is never going to go below 0. So it looks like the lowest possible y value is 0. The highest possible y value, it looks like it's going to shoot up towards infinity, and that's indeed what it's going to do. 0 to infinity. And then finally what we're going to do is we're going to go ahead and say that there's an asymptote. An asymptote is a value that it approaches but it never really reaches. This function appears to try to reach 0 on the x-axis. Okay? Remember, a horizontal line has the equation y equals that constant value. So in this case, the asymptote is going to be at y equals 0. So this is a basic exponential function with its properties. All right, so what I'm going to ask is take a pause, right, and maybe you can go ahead and graph an exponential function. Right? So for example, like I said, pause the video right now and try to graph the function g at x is going to be equal to, let's say, 1/3 to the x power. All right, so hopefully you paused it and you try to graph this thing. And let's see if you got to what the graph looks like, and also let's see if you can identify what the domain, the range, and any asymptotes for this function might be. All right. Once again, what you should do is start by making a table of values. You should probably always rely on your -2, your -1, your 0, your 1, and your 2. All very basic values to utilize, nothing too big, nothing too small. I always say work from the bottom up. Work with the positive values, then work with the negatives. If I substitute 2 back in for x, I get 1/3 squared, which just means 1/3 times 1/3. 1/3 times 1/3 is 1/9. If you don't believe me, throw it in your calculator. 1/3 to the first power. Anything to the first is an identity. It's itself. So 1/3 to the first is 1/3. As we saw in the previous example, 1/3 to the 0 power. Anything to the 0 is 1, except for 0 to the 0, which is an indeterminate form. As we saw in the previous, when we take something to a negative power, we take the reciprocal and then we get rid of the negative. So this 1/3 to the -1 really becomes 3 to the first, since the reciprocal of 1/3 is just 3 over 1. 3 over 1 is 3. 3 to the first is 3. And then finally, 1/3 to the -2. Okay. You're going to flip over your 1/3. It's going to become a 3. The negative drops off, and that just becomes 9. So those are our values for our table that we can go ahead and construct for our exponential of 1/3 to the x. Let's plot, and then maybe look at some of the similarities and differences of the 2 to the x that we just looked at. And as you graph it, think about what the domain and the range might be for this. -2, 9. Left 2, up 9. So right about here. Then we're going to have -1, 3. Left 1, up 3. We have 0, 1. We have 1, 1/3. So it's going to be right about here. And then finally, 2, 1, 9. Okay. Now, there are some similarities between what we just had with the 2 to the x and the graph that we have here. One of the similarities is I can't draw either of them apparently too well. Okay, but other than that, hopefully we get the idea of what this looks like. Okay. If I was to ask the domain of this function, think for a second, what would you say about the domain? I would think that it's going to keep going left forever, it's going to keep going right forever. So I would think it's going to go from negative infinity to positive infinity. There's no gaps in this. It just keeps going on forever. Think for a moment about the range. What do you think the range might be for this? In other words, how low does it go? How high does it go? Just like the previous, it looks like that it's not going to go any lower than 0. It looks like it's just going to keep shooting up towards infinity. So 0 to infinity. What do you think about the horizontal asymptote? Do you think it still has the horizontal asymptote of y equals 0? Well, it looks like, even from my very crude construction, that these points keep getting lower and lower towards 0, but they never really reach it. So once again, if I was to ask for an asymptote, you would tell me that y equals 0 is indeed an asymptote of this exponential function. What we see in both examples is that the domain and range are the same as well as the asymptote, which is generally true of most families of functions. They usually have very similar properties. That's why they're called families of functions. So what you may wish to do is to take a break, look over your assignment, or assignment number 2, and then see if you guys can go ahead and figure out the graph of the 3 to the x. Okay, and then maybe do some transformations.